Hi, my name is Naved Haq, and this is my Lab 1 presentation for Physics 1. Today, I'll be presenting my constant velocity lab, where I analyze the motion of a marker to see if it followed the predictions of a constant velocity model. The purpose of this lab was to study an object moving at a constant speed without changing direction. I wanted to see how closely its real-life motion matched to what theoretical modeling could predict. To do this, I used Tracker to collect actual position and time data from a video of the marker rolling across the table. I then used GlowScript with VPython to build a model that simulated how the marker should move if it had a perfect constant velocity. The whole idea is based off of Newton's second law, which is F equals ma. If the acceleration is zero, then the net force also has to be zero, which are the conditions for constant velocity. In the end, I compared my model's results to the real data, and they matched very closely. The theoretical model that I used was based on Newton's second law, which says that force equals mass times acceleration. Since I wanted zero net force, I needed to eliminate friction as much as possible, so I rolled a marker, which creates very little friction compared to sliding, so this was one assumption that I had. I used the position update equation, x equals x naught plus vt, which only works when acceleration is zero, or else you would have to introduce another term. This allowed me to predict where the marker would be at each moment in time using GlowScript. I also assumed the table was perfectly level and that air resistance was negligible, so no vertical or drag forces would interfere, with the assumption that acceleration equals zero. These assumptions helped isolate the motion and made sure that my model only needed to account for position, velocity, and time. I then used this model to generate predicted data that I could directly compare to my experimental data. In this experiment, my system was just the marker itself, and the surroundings included everything else, including the table, air, and the ruler that I used. I placed the ruler in the background for distance reference, and then I rolled a marker across the table to create a frictionless environment, and I filmed it moving in a straight line with a still camera. I then imported this video into Tracker on my computer, which let me mark the marker's position frame by frame to get data for its motion over time. Then, using GlowScript, I created a computational model which was based off the Lab 1 starter code. In the code, I defined the marker's initial position and velocity, and I then used a time loop, which you can see here, that repeatedly updated the position using the position update equation that I showed earlier. I then set the loop to run for 0.733 seconds, which is the same length as my tracker video, so the two datasets would align. Since the net force was zero, the velocity never changed during the loop. The program printed a list of time and position values, which I later plotted to compare directly to my tracker data. This graph shows the comparison between my two datasets. The blue points are from Tracker and the orange line is from my GlowScript model, and they line up almost perfectly. The reason it's a straight line is because there's so many data points that it's a bunch of points all connected. This shows that the marker's motion was accurately described by the constant velocity model. There are some small possible errors that could come from clicking slightly off center of the marker in Tracker, or from small timing variations between video frames, but these were very minor. If I reverse the axes, the slope would become negative, but its magnitude, which represents the speed, would remain the same. The linear shape of the graph confirms that the marker's position changed by equal amounts each second, which means that it was moving at a constant velocity. Overall, my experimental observations matched my computational model based on the assumption that net force equals zero. This means that the marker was in dynamic equilibrium. It kept moving at constant velocity without accelerating. It's important to remember that zero net force doesn't mean that there's no net force at all. It just means that all the forces cancel each other through vector addition. The graph shows that when forces are balanced, a constant velocity model can accurately predict motion of a real-world object. Thank you for listening to my presentation.